Welcome to today's explainer. Have you ever actually stopped, looked up at the sky, and wondered what is really going on up there? Today, we're going to look at the Earth's atmosphere, but not just as some passive blanket of air. We're going to look at it as a massive, incredibly complex, and interconnected planetary engine. It literally has fuel, it has moving gears, and it produces an output that dictates how we live our lives every single day.
Okay, let's dive into this. We'll be hitting 5 main areas today: weather versus climate, inside Earth's atmosphere, turning up the heat, pressure, winds, and rain, and finally, shaping our climate. Section 1. Weather versus climate, the engine's output. People mix these two terms up all the time, right? But there is a very distinct difference. Weather is dynamic. It's the exact atmospheric condition of a specific place at a specific time. It can literally change from hour to hour. Climate, on the other hand, well, that's the sum total. It's the generalized average of those weather conditions over a really long period of time. To use a classic analogy, climate is what you have in your closet. Weather is what you actually wear today. But remember, the fundamental elements that determine both of these are exactly the same: temperature, atmospheric pressure, wind, and humidity. Moving on to Section 2, inside Earth's atmosphere, the machine's casing. So our atmosphere is this brilliant, highly precise mixture that perfectly sustains life. It's actually almost entirely nitrogen, sitting at 78%, followed by the oxygen we need to breathe at 21%. But look at that tiny sliver of trace gases. We're talking about carbon dioxide at just 0.04%. Now, even though it's a microscopic fraction of the whole shebang, that 0.04% is absolutely crucial. Without it, plants couldn't perform photosynthesis and the whole system would break down.
And this mixture isn't just one big uniform cloud of gas, it is highly structured. If we were to take a journey straight upward from the ground, we'd travel through 5 distinct layers. We start right here in the troposphere. That's where we live, and it's where all weather actually happens. Above that is the stratosphere, and then we hit the mesosphere. The mesosphere is basically the atmosphere's bodyguard. It's the exact layer where meteorites burn up as shooting stars before they can crash into the Earth. Finally, we travel through the thermosphere and out into the exosphere, which just sort of gradually fades away into the vacuum of space.
Now, as we travel upward through that very first layer, the troposphere, we experience a very strict rule of nature called the normal lapse rate. For every 165 meters of altitude you gain, the temperature reliably drops by exactly 1 degree Celsius. Why? Well, because as you move up, the envelope of air literally gets thinner. There are fewer gas particles available to hold on to any heat, so it rapidly gets colder the higher you go.
Section 3. Turning up the heat, the engine's fuel.
So this planetary engine is entirely powered by the sun, specifically a concept called solar insolation. The sun radiates massive amounts of energy in all directions, but the Earth only manages to catch a tiny, tiny fraction of it. And here is the absolutely crucial point. The sun doesn't actually heat the air directly. Solar radiation passes right through the atmosphere and heats the ground first. Think of a scorching asphalt parking lot in the middle of summer. It's that heated ground radiating upward that warms the air above it, which is what sets our entire atmospheric engine into motion.
Once that ground is nice and hot, the planet transfers the heat upwards and outwards through 4 specific processes. First up is radiation, where the Earth directly radiates heat back up into the air. Second is conduction, where the air literally touches the warm ground and heats up through direct contact. Third is convection. That's where that warmed air becomes lighter and rises, creating vertical hot air currents. And finally, advection, which is the horizontal transfer of heat. Basically, that's just wind blowing warm air into a cooler region.
But because the Earth is a sphere, all that solar fuel doesn't hit the ground evenly. The equator gets direct, super intense rays, while the poles get these slanting, much weaker rays. This creates 3 permanent global temperature belts. You have the torrid zone right around the equator, which is intensely hot with heavy rainfall. Moving outward, we find the temperate zones. These enjoy pretty moderate climates thanks to those slanting sun rays. And at the far extremes, we have the frigid zones at the poles. They receive so little warmth that the ground is often permanently frozen, which we call permafrost.
Let's look at Section 4, pressure, winds, and rain, the moving parts.
Okay, so variations in heat create variations in atmospheric pressure, and nature absolutely hates an imbalance. So air wants to move from areas of high pressure to areas of low pressure to even things out. We call that moving air wind, and wind acts on 3 different scales. First, we have permanent planetary winds like the trade winds, which blow constantly all year long, moving hot air away from the equator.
Then we have periodic winds. Think seasonal monsoons that change direction entirely depending on the time of year. And finally, we have highly specific local winds.
And this brilliantly illustrates how local winds can completely define a region's identity. Take a look at these examples. The Khamsin brings intensely hot, dry conditions to Egypt. The Sirocco blasts hot air directly from the Sahara over to the Mediterranean. Blizzards define the freezing tundras, while the infamous Santa Ana winds drive uniquely hot, parched conditions right across Southern California.
But wind doesn't just push hot and cold air around. It moves water. Let's clear up a really common confusion about humidity. Absolute humidity is the sheer physical volume of water vapor sitting in a specific block of air. But when weather forecasts talk about humidity, they're actually talking about relative humidity. That's a ratio. It's the percentage of moisture currently in the air compared to the absolute maximum amount it could physically hold. Think of the air like a sponge. Relative humidity is just how full that sponge is before it can't take any more and starts dripping as rain.
And when the air hits 100% relative humidity, the engine essentially squeezes the water out through three distinct mechanical processes. Convectional rainfall happens near the equator, when the hot ground forces moist air straight up until it cools and condenses. Relief rainfall happens when moisture-laden winds hit a physical barrier, like a mountain, and are forced upward. And cyclonic rainfall occurs when a massive front of warm air is violently forced upward by an encroaching wall of intense cold air.
Finally, Section 5, Shaping Our Climate, Local Customization.
So this massive global climate engine gets heavily customized by local geography. There are 6 major factors at play here. Latitude determines your baseline solar heat. Altitude cools things down. Your distance from the sea determines if your climate is moderate, what we call a maritime climate, or if it's prone to extreme temperature swings, known as a continental climate. Add in the flow of warm or cold ocean currents, the direction of prevailing winds, and the amount of vegetation covering the ground, and you have a deeply complex, incredibly localized system.
Let's look at a wild example of how these factors can actually fight each other. Mount Kilimanjaro is located in Tanzania, right near the equator. So based on latitude alone, it should be sweltering hot. And at its base, it absolutely is. But because it rises nearly 6,000 meters into the sky, its altitude completely overrides its latitude. The air gets so thin up there that the summit is perpetually freezing and snow-capped, despite being essentially on the equator.
Or consider just how totally interconnected this atmospheric machine is. What happens in one place is carried by the gears of the engine to somewhere else entirely. Here's a perfect real-world example. When fresh snow falls up in the mountainous region of Shimla, cold winds pick up that chill, travel horizontally, through that process of advection we learned about earlier, and actually drop the winter temperatures in the distant city of Delhi. The atmosphere connects us all, no matter where we are.
From the precise mixture of invisible gases that sustain life, to the sun heating the dirt beneath our feet, to the massive pressure systems moving literal oceans of air, our atmosphere is a true marvel of planetary engineering. So I want to leave you with this final thought. Next time you step out your front door, take a moment to really look up and feel the air. Ask yourself, which gears of this massive atmospheric engine are spinning right now to drive your weather today? Keep exploring, and thanks for joining me on today's Explainer.